Hello everyone, let's analyze. So today we're going to talk about the implicit function theorem. So you may remember from Calculus 1 taking implicit derivatives. That was useful for computing the slope of some implicitly defined curve in two-dimensional space that wasn't necessarily a function like a circle or an ellipse or the trisectics of Maclaurin. Maybe you don't remember that implicit curve. I remember it because of the epic name. Go and Google it. I'll wait. Okay, are you back? So just to stir up our recollection, let's take a look at a common implicit function that we're all familiar with. The circle. So there are a lot of ways of defining a circle. We can parameterize it by theta. We could say the set of all two-dimensional coordinates that are equidistant from some center point. But another way that we can do it is we can consider the mapping from 2 dimensions to 1 dimension given by x squared plus y squared minus 1, and consider all of those points x and y for which x squared plus y squared minus 1 equals 0. In other words, we're considering a level set. What is the level set of the function f of x, y? What are all the x and y pairs for which x squared plus y squared minus 1 is equal to 0? And hopefully we recognize that as the circle of radius 1. There's our circle there. So that red circle is again all x and y pairs for which f of x comma y is equal to 0. So that's one way of defining a circle. Of course, if we consider the circle as a curve in two-dimensional space, we can't in its entirety think of it as a function because it would fail the vertical line test. Now, of course, we could think of the top part as a function. We could say f plus is the square root of 1 minus x squared. That'll give us a semicircle, the top semicircle. And f of x comma f plus of x is 0 because the graph x and f plus of x is on the circle, and every point on the circle satisfies f of my coordinates is equal to 0. Similarly, the bottom half could be expressed as a function. We can have f minus is negative square root of 1 minus x squared. So there is no function that captures the implicitly defined curve in its entirety, but there is a function that captures different parts of my implicitly defined curve. So consider the question, for an ordered pair, x naught, y naught, on the curve, meaning f of x naught, y naught is 0, is there a unique function, y equals f of x, such that f of x comma f of x equals 0? In other words, the graph of the function y equals f of x is on the curve defined by the 0 level set of x, f of x comma y. And the function passes through the ordered pair x naught, y naught. Well, in the example we see before us, yes, right? For a point here on the curve, f plus passes through the point and is on the level set, f of x comma f plus is 0. And for a point here on the curve, f minus passes through that pair, ordered pair, and f of x comma f minus is on my implicitly defined curve. So the answer is yes, unless x naught is here or here. Well, what went wrong? Well, both f plus and f minus capture the ordered pair. So I don't have a unique function passing through this ordered pair here or here that's on a curve. I have two. Now notice that neither f plus nor f minus is differentiable at the point where things went wrong because the tangent line is vertical. In other words, if I took the derivative of f plus or f minus with respect to x at these points, right, I would get infinity. That is, if I took the limit as x approaches 1 or negative 1 of either f plus or f minus, then I would head off towards infinity. Another way of pointing out that the tangent line is vertical is that the derivative of f with respect to y at those points is 0. We can take that derivative. The derivative of f with respect to y is 2y, and if y is 0, I get 0. So if the derivative of f with respect to y is 0, then the tangent line of this graph, that is the graph of the circle, is vertical. So let's keep this example and the dynamics happening here in mind as we work our way through the implicit function theorem in multiple dimensions. Another application for implicitly defined functions might be solving an initial value problem that is of this sort: m of x plus n of y times the derivative of y with respect to x equals 0, where I have an initial condition y of x not equals y naught. So if you have ODEs fresh in your mind, you might have already recognized that differential equation as being separable. And because it's separable, you can separate and anti-differentiate to get an implicitly defined solution. In other words, every pair of x and y that satisfy this equation, f of xy, where f of xy is defined in this way, is equal to 0, solves my initial value problem. But is there a unique function y of x that satisfies this implicitly defined relationship? In other words, something that passes through my initial condition and f of x comma y of x is 0. Well, note that the derivative of f with respect to y evaluated at x naught y naught, and of course we can take this expression, take a derivative with respect to y, we would get n of y, and if I evaluate at y equals to y naught, we get n of y naught. So if the last example is in the indication, we don't want n of y naught to be 0. If n of y naught is 0, then from the precedent in the last example, there may not be a unique function y of x that solves the initial value problem and passes through my initial condition. There may be none, there may be more than one. So before we get to the implicit function theorem, in other words, when does a mapping like the mapping from R2 to R that we saw in the case of the circle, when does a mapping, when set to a constant, define some implicit function? So before we get to that theorem, let's enjoy a prelude. Suppose f maps some open set in Rm by Rn. In other words, f maps a vector in Rm plus a vector in Rn to a vector in Rn. And suppose f is class C1. Suppose also that there are open sets V in Rm, W in Rn, so that the cross product V and W is contained in U, the domain of f. And suppose also that there is a function g mapping V to W, that's class C1, for which f of x comma g of x is 0. In other words, g would be an implicitly defined function. G maps x to g of x. And it's on the curve kind of defined by the level set of f at the level 0. So there is an implicitly, now here we're assuming that there's an implicitly defined function of class C1 on the curve. Furthermore, the derivative of f with respect to x, evaluated at x comma g of x, plus the derivative of f with respect to y, evaluated at x comma g of x, times the derivative of g is 0. Now, of course, if g is my implicitly defined function, well, what's the derivative of g? Well, if this matrix here is invertible, when evaluated at x, g of x, then the derivative of g is equal to this, right? We just solve for the derivative of g, subtract this, and multiply by the inverse of this matrix on both sides, and we get this expression. Now, again, here in this theorem, we're assuming quite a bit, right? We're assuming that if I set f of x comma y equal to 0, and that does define an implicitly defined function, then if so, the derivative is given by this information here. So let's prove that. Suppose H maps V to V by W. And just so that I remember, what is V? Right, V is in Rm. V by W is in U, the domain of F. So H maps V to V by W, and V by W is contained in the domain of F. So H is defined by H of x equals x comma G of x. So H of x maps, well, x to x, that's a pretty straightforward map, and x to g of x. G of x is the implicitly defined function we're assuming exists. Now, f of x comma g of x is 0. We've assumed that. And, well, x comma g of x, that's h. So, in fact, this is the composition of f and h. So from the chain rule, the derivative of the composition of f and h is given by this. Now, by the way, since this is equal to 0, the derivative of this is equal to the derivative of 0. So we apply the chain rule. The derivative of this is the derivative of f at h times the derivative of h. Now, the derivative of f at h is the derivative of f at, well, what h is defined to be. So x comma g of x. The derivative of h, well, the derivative of h with respect to x is just the identity. And the derivative of g is, well, the derivative of g. So I get the derivative of my composition is equal to this times this. Now, what is this? Well, that's just the derivative of f with respect to x, the derivative of f with respect to y. Remember, f maps a vector in x and a vector in y. Right, so f maps a vector x, a vector y to another vector. So if I'm going to take a derivative of f, I have to take a derivative with respect to all of its inputs. So instead of thinking of f as a function that maps Rn by Rm, I'm thinking of it as a function that maps Rn plus m. So the derivative of f, in other words, is the derivative of f with respect to x, and then the derivative of f with respect to y. So if I multiply this matrix times this matrix, I get this. This component times this component, plus this component times this component. Now remember that the derivative of this is 0, because this is 0. So, of course, the identity is just the identity. It doesn't change anything. So I get that this term here equals 0 for all x and v. Remember, V is the domain of G. Right? G is my implicitly defined function that maps x to g of x. And it's on the level set of x comma y equal to 0. So I have the expression I want. And if the derivative of this term is non-zero, then I can solve for the derivative of g, giving me this. Okay, so on to the main event. So suppose f maps a open subset of Rm by Rn to Rn. In other words, f takes an ordered pair of vectors, the first vector being an Rm and the second vector being an Rn, and f maps that ordered pair of vectors to Rn. Suppose f is class C1, and suppose that the ordered pair AB, meaning A is a m-dimensional vector and B is an n-dimensional vector. Suppose that the ordered pair is in the 0 level set of f. In other words, f of AB is 0. And also suppose that the derivative with respect to y of f, when evaluated at that ordered pair, is non-zero indeterminate. Right? I say indeterminate because now we're dealing with a matrix. And that matrix is square because I'm taking a derivative with respect to y, and y is n-dimensional. So I'm considering this to be fixed, so I have a mapping from Rn to Rn. So its derivative is square, and I'm supposing that it is a non-singular matrix. Right? That's the matrix analog of being non-zero, essentially. So if my hypothesis is true, then there's an open and connected subset V in Rm and W in Rn, and a unique class C1 function G that maps V to W that is implicitly defined by the relationship f of x comma y is equal to 0. In other words, f of x comma g of x is 0. G of A is B. In other words, the graph of G passes through the ordered pair AB. And furthermore, the derivative of G is given by this relationship. Now, before we prove it, let's take a look at an example, just so we can get our bearings of how to maneuver and work with the results of this theorem. So suppose f maps an ordered pair of vectors from R2, so two vectors in R2, to a vector in R2. And it's given by this expression. So again, I can think of f as a function of x and y, where x has two components and y has two components. I can also think of f as a mapping of a four-dimensional vector to a two-dimensional vector, where that four-dimensional vector has entries x1, x2, y1, y2. So f is given by this. If I consider all ordered pairs x and y such that f of x comma y is equal to 0, does that give me a class C1 function map from x to the y defined by x? So let's consider a point. Let's consider the ordered pair of vectors 1, 1 and 1, 1. So we can check that that ordered pair indeed satisfies f of a comma b is equal to 0. So we can also see that f is clearly class 1 because I can take a derivative in every direction and get something that's still continuous. In fact, the derivative is this 2 by 4 matrix. Again, 2 by 4 because the domain of f can be thought of as four-dimensional. So if I take the derivative of f and evaluate at this ordered pair of vectors, in other words, x1 is 1, x2 is 1, y1 is 1, y2 is 1, I get this matrix. Now, the derivative of f with respect to x, that's this first 2 by 2 block. And evaluated at this ordered pair, I get this 2 by 2 block. And the derivative of f with respect to y is this 2 by 2 block. If I evaluate at the ordered pair of 1, 1, and 1, 1, I get this 2 by 2 block. Furthermore, the determinant of this 2 by 2 block is -4, and -4, last time I checked, is not 0. It's -4. So the hypothesis of the implicit function theorem is satisfied. And in this example, we're supposing it's true. So if the implicit function theorem is true, and it is true, I'll prove it to you shortly. What does that buy us? Well, what it means is that there are open subsets V and W, where V contains A and W contains B, and there's a unique class C1 function that maps V to W and maps A to B. Furthermore, this unique function G is implicitly defined by the relationship f of x comma y is equal to 0. In other words, y equals g of x is on that level set. Furthermore, I can tell you exactly what the derivative of g is at the point that satisfied my hypothesis. The derivative of g at a is given by the inverse, the negative inverse, of the derivative of f with respect to y at my ordered pair times the derivative of f with respect to x at my ordered pair. And of course, we know what those matrices are because we computed them already. So I get the negative inverse of this times this, which I went ahead and calculated beforehand. It's equal to this. I didn't do it in my head just now. So in particular, I know what the derivative of g is with respect to x1, with respect to x2, right? Both components of g, because g maps a vector in R2 to a vector in R2. Therefore, I know all the partial derivatives of g at the ordered pair 1, 1. So this follows from the result of the implicit function theorem. So let's prove it. Let's get back to our regularly scheduled proof of the implicit function theorem. So again, we're going to use this auxiliary function h. H maps u, and remember u is the domain of f. So u is an open subset considering of ordered vectors in Rm to Rn. And it's going to map it to ordered vectors, an ordered pair of vectors in Rm by Rn. And h is defined as h of x comma y is equal to x comma f of x comma y. So x is a m-dimensional vector, y is a n-dimensional vector. X gets mapped to x, y gets mapped to f of x comma y, which is a n-dimensional vector. And h is defined wherever f of x comma y is defined, because u is the domain of f. Now remember, f of a comma b is 0, right? The ordered pair AB is on the level set. So remember, the ordered pair AB is on the 0 level set of f. In other words, f of a comma b is 0, and well, a just gets mapped to a. Furthermore, the derivative of h is given by, well, let's consider the derivative of h1, this entry. So the derivative of x with respect to x, the identity. The derivative of x with respect to y, 0. The derivative of f with respect to x, the derivative of f with respect to y. The determinant of this matrix is this matrix times this matrix, which is of course just this matrix. And we've assumed that the derivative of this matrix is not 0. Therefore, H satisfies the hypothesis of the inverse mapping theorem. The inverse mapping theorem was in the previous lecture, so you might want to pause here and review the hypothesis of that theorem. If you do, you'll see that RH indeed satisfies the hypothesis of the inverse mapping theorem, meaning it's got an inverse, specifically in an open set containing this point. In other words, there's an open set T containing this point, and what is this point equal to? Well, H of A comma B. And there's an open set containing A, B, for which H of S equals T. In other words, H maps A to B to A0. So there's an open set S containing AB that gets mapped to T, which contains this point. And that mapping is invertible. And the inverse has the same continuity class as H. So H maps S to T, H inverse maps T to S, and the inverse is unique. So within S is an open quote-unquote rectangle that contains AB. So in other words, A and B is in V by W. So V is some open set in Rm, W is some open set in Rn. So if M and N were 1, we could think of V and W as kind of like open intervals, for example. This is why I use rectangle in quotes. So V is some open subset of Rm, W is some open subset of Rn, and V by W contains A to B, and V by W is in S, the domain of H where I have invertibility. So since H of V by W is contained in H of S, which equals T, H of V by W is contained in T. Furthermore, H inverse maps the image of H. Furthermore, H inverse maps the image of V by W under H back to V by W, because H inverse undoes H. Now, since H of x, y is, by definition, x comma f of x comma y, xy is equal to H inverse of x comma f of x comma y. Now, it follows Now, what happens if I evaluate H inverse at some x and y? I know what happens if I evaluate H at some x and y, but what if I evaluate H inverse at some x and y, where x and y is contained in the image of V by W under H? Well, notice that H inverse of x gets mapped to x. But how does H inverse map y? Well, H inverse of x is x, and H inverse of y depends on x and y, right? Some function of x and y. What is little h? We don't know. But we know that little h is C1 because H inverse is C1. H inverse is C1 by the inverse mapping theorem. And since this h has to depend on x and y, and where is x and y? Well, x and y are in H of V by W, and specifically gets mapped to W. It gets mapped to the second pair, right? It gets mapped to W because this is the ordered pair that's in V by W. X is in V, and H of x comma y is in W. Now, suppose G of x, and G is going to map V to W. G is our implicitly defined function that we are looking for. Suppose G of x equals H of x comma 0. Well, if that were true, then h inverse of x comma 0 equals x comma h of x comma 0. And h of x comma 0 is g. That's what we define g to be. Well, that implies that if I take h of both sides, h of this and h of this, I get x comma 0 equals h of x comma h of x comma 0. But h of x comma 0 is, well, h of x comma 0 is g of x. And what is h? Well, remember, h is x comma f of x comma y. So h of x comma h of x comma 0, x f of x comma g of x. So if this ordered pair equals this ordered pair, that means this second vector in the pair 0 equals this second vector in the pair f of x comma g of x for all x in this open subset V. So I have found a function g so that the graph x comma g of x is on the level set of x comma y equal to 0. So are we done? Did we do it? Well, let's see. Does g of a equal b? Is the map defined by g from v to w uniquely defined? We know that h of a comma b, by definition, is a f of a comma b, meaning that a comma b is equal to h inverse of a comma f of a comma b. F of a comma b is 0. And from our previous work, we know that this is a comma h of a comma 0, because that's what h is defined to be. Little h tells me how the inverse maps the second vector in my pair. And well, this is equal to g of a. So if this ordered pair equals this ordered pair, b equals g of a. So does g of a equal b? Yes. Now, since h inverse is a uniquely defined inverse, and h inverse of x0 equals x comma g of x, then if I take h of both sides, I get h of x comma g of x equals, well, x comma 0, but also how is h defined? H is x comma f of x comma g of x. And these are all one-to-one mappings that are guaranteed by the inverse function theorem. Therefore, we're assured of the uniqueness of G. Now we're done. Well, that's it for today.